So this is the course Analog IC Design. So I am Nagendra Krishnapura, and this is my web page. You can go to the website and see this, and this is my email. I already sent you email about the course. I hope that all of you got it. I think the Moodle page is not set up yet. It will be set up shortly, and all the material can be accessed from Moodle. So this, I'll spend some time introducing this course, the motivation for a course like this. It is titled Analog IC Design. First, I'll talk about analog, what it is. I think you already know. I think all of you have taken the analog circuits course. So you know what analog is, what an analog signal is, and any circuit that processes analog signals is an analog circuit. And those implemented on integrated circuits are analog integrated circuits. Okay. So why do we need this? This is the picture of most modern signal processing systems. There is a very large digital signal processing core. Why is it? Why is it that digital has become so big? What is the big deal? Of what? Digital? Okay. What about? Okay. Okay. Yeah, actually it is storage and computation. The storage, basically storing any other type analog signals is very difficult, whereas storing digital signals is very easy. So you have large amounts of storage and then of course processing on that data. Now, of course, the real world signals in most cases are analog. It could be audio, it could be radio signals or anything else. So you need interface circuits between the digital signal processing core and the analog world. So on one side you have sensors such as the microphone into which I'm speaking, or if you have, I mean, all of you have mobiles, so you will be receiving signals at the antenna and so on. And you have to process those things. And also on the other side, I mean, again, the loudspeaker is putting out audio. So from the digital processing core, it has to take the signal, convert to analog and convert it to audio signal, or let's say in case of a radio into radio frequency signals, right? Now these have continuous time and continuous amplitude, and in all these interface circuitry, you have analog circuits, right? You need analog circuits for all of them, and they're actually crucial parts of the system. And one of you mentioned that the noise margin in digital ICs is high. That is true, but that is after converting it to digital form. So in the process of converting from analog to digital, if you end up having too much noise, and it doesn't matter how much the noise margin of the digital is, that noise will be in digital form also. Okay. So we will study all these things, noise of analog circuits, how to analyze them, how to minimize them, and so on. Right. So this just lists the same thing. Mainly, I mean, the interface circuitry have analog to digital conversion and digital to analog conversion. Both are analog circuits. And then amplification, that is, you have a continuous time signal, you want a larger continuous time signal out. That also is an analog circuit. And also, it turns out that in a given technology, as you go to higher and higher frequencies, it becomes harder and harder to make any circuit, and in particular, digital circuits. So there is some signal processing at the highest of frequencies, which tends to be still in analog. Or it could be that you can do it in digital, but it consumes a higher power. So you have to do it in analog. These things are there. So that also, and this boundary keeps moving with technology. As technology progresses, the highest frequency signal that can be processed keeps on going up. Highest frequency signal keeps on going up, so that boundary keeps moving up as well. That is, the highest frequency at which you can process digital signals keeps increasing also. Clearly, circuit design is not done properly here. And then you have power management. That is, you have lots of voltage references, voltage regulators, and so on. All of you are familiar with these voltage references? I think in analog circuits, were you introduced to them? Yeah. So first of all, I mean, you will see as we go on, you will have lots of circuits, different, different circuits are biased differently and things like that. And of course, your mobile has only one battery. From that, you have to generate all the voltages, and all these voltage levels are different. For the display, it will be different. For the processor, it will be different, and so on. Okay. But you have one battery whose voltage keeps changing slowly with time as it discharges. And from that, you have to generate all these things. And such circuits are called power management circuits. In fact, one of our colleagues is a power management specialist. There is power management IC, also a course in another semester. And then you have oscillators and phase lock loops. You know that how do digital circuits work? You have sequential state machines, and how does it go from state to state? It does it at the edges of some periodic clock. Now, to generate that clock, you need these clocking circuitry, which involve oscillators and phase lock loops. Okay, and these power management circuits and oscillators, you find them even on quote unquote purely digital chips. I mean, if you have a microprocessor, you don't think of it as an analog IC. It is of course a digital IC, but you have this clocking circuitry and power management circuitry even in that. In fact, some of them have very sophisticated power management circuitry, so that you use as little energy as possible for doing the given computation. Okay. Just to show you some chips, this is some image sensor. These are all like really old examples, but the general theme applies. You have the imager in the middle. That, I mean, is some sort of analog. Basically, it takes light and then gives you some signal. And after that, you have this processing circuitry. You have the analog to digital converter, which gives you the image data in digital form. And then you have some noise cancellation circuit, timing generator, what I just mentioned, this clocking and so on. And power management, you have the voltage regulator here. Okay, this actually is a pretty analog heavy chip. And you have a radio transceiver, and actually the present day transceivers are even more sophisticated than this. You know, you must have heard of so many different bands and so on, and your radio works at many bands. But how does it work? Basically, there are so many different radios for each band, or each radio caters to a couple of bands, and then you have tens of bands. So you have lots and lots of transceiver circuits on the same IC. Okay, this is also an analog heavy example. Now this is a DRAM. Like I said, this of course is a sort of digital chip, but you have the power management circuitry here, and in the middle you will also have this clocking circuitry. Okay. Now, of course, what else is the motivation to get a job? That is a very important motivation. So the good thing is that analog IC design is considered difficult, which also means that if you learn it, it's harder for somebody else to take away your job. So, and there is a lot of activity going on now, and of course, with the recent semiconductor push, we expect that more and more jobs will be in India, more and more design jobs. And these pay well also. So if you learn something well, I mean, if you learn art well, maybe you'll be a starving artist, but if you learn analog IC design well, you won't be starving for sure. Okay. So it's an interesting and profitable activity. So that's something that you can enjoy, right? Now, what are the goals of this course? First, it's analog IC design, and you already have grounding in analog circuits. So it will build on what you know. The main thing is you have to learn to design negative feedback circuits on CMOS ICs. And that is a vehicle for learning everything else about analog design also. So if you learn this, you will learn about circuit design. And in the previous ones, you would have learned some of this stuff, op amps and so on, but without a particular emphasis on ICs. So that's what we'll do here. What is a negative feedback circuit? You have negative feedback for controlling the output. And these are used in amplifiers, voltage references, voltage regulators, biasing circuits, and so on. So if you take a modern analog IC, there'll be bazillion negative feedback loops inside them. There may be a main signal processing circuit with feedback. and within that there may be op amps each with their own feedback, and each op amp is biased with its biasing circuitry, and the biasing circuitry may have their own feedback and so on. Okay, so feedback is used for accurate control of any quantity, and that's what we'll use them for also. And then you all have phase lock loops and filters. These we will get to if we have time. We'll see. Yeah. Analog computation we won't treat here. So it is sort of coming back. Earlier, there used to be analog computation in the form of implementing differential equation solvers using analog circuits, right? So you have capacitors and inductors. So you can, by connecting capacitors, inductors, and other elements, you can form circuits that solve differential equations. Actually, every filter is like that. Every filter is described by a differential equation. Now, of course, to be general, you also have to include nonlinearity. Those things went out of fashion because of limited accuracy and much improved accuracy of analog computers. Now they are coming back. We won't treat them in this course, but the circuit principles we have will apply there also. Okay. There are two types of analog computers being thought about. One is some sort of analog differential equation solver, which gives you an approximate solution. Because you know that any nonlinear equation, nonlinear differential equation, it is solved by iteration. There is no closed form solution. So for any iteration, you have an initial condition. First of all, in most cases, there is no guarantee that you will get the exact solution. You start from somewhere, you iterate a certain number of times, and you get closer and closer to the solution, hopefully. And if you start with a good initial condition that is already close to the solution, then it will be better. The accuracy will be better. So the idea is that if you start from the solution of an analog computer as the initial condition for the digital computer, convergence may be faster and accuracy will be better and so on. And there is another type of analog computation, which is mainly for calculating linear combinations. Okay. Now, of course, there is ML and AI are everywhere, right? If I had put analog IC design for ML, this room would not be sufficient to hold all the students. So there, if you even if you don't know about this, you will see that a big operation is linear combination and truncation or some approximation of that. Okay, that is, you have all these layers in a neural network, and going from one layer to another, you have this linear combination of the outputs of one layer by some weights. Now you can of course calculate have each of these quantities, both the weights and the outputs of the layer, in full digital form, 16 bits or 32 bits or whatever. It turns out that you don't need that kind of accuracy. Okay, what you care about is the output of the that weighted summation. So the idea again is, especially for, and of course the number of computations in a neural network is very large in any realistic form, right? So the idea is that because poor accuracy is sufficient, you can calculate this weighted summation in analog and get the final output instead of digitizing each one. And maybe that final output you digitize. This way you will save power. And this is mainly intended for what are known as edge devices, things that work on batteries and so on. Okay. So that is there. Again, for that, I mean, the specifics of the circuit we won't deal with, but whatever circuit design techniques we use, you can use them there also. Okay. Now, of course, to be able to go through this course, you need to know these prerequisite concepts. Circuit analysis, hopefully you are doing it till last month in the previous course, so you still remember this. Small signal and large signal analysis, and then of course tools for linear analysis like Laplace transforms and frequency response, body plots, differential equations, and so on. The ideal op amp circuits, I assume you know, and op amp non-idealities, the main ones. And you should also know something about single transistor amplifiers, all the basic single transistor amplifiers and differential pairs. We'll take those as starting point and go from there. Okay. And of course, in terms of prerequisite courses, whoever did their bachelor's here would have gone through these. Otherwise, you would have gone through these in some other place. So this is basically what you need to know. If you feel that you're a little bit shaky with some circuit analysis, there are old recorded lectures with There's Laplace transform tutorials and so on. So please go through them. Make sure that you're fluent with them. Now, what will we see? I'll start with this is analog integrated circuit design. So I'll start with components that are available on an IC, right? Otherwise, I mean, they are the same components, but there are some restrictions to either their values or how they are connected and things like that. Okay. So you have the MOS transistor, and MOS transistor equations you already know. By the way, are all of you familiar with weak inversion and subthreshold operation of MOS transistors? Was it taught in the previous analog circuits? Okay, we'll go through that. I think all of you would be familiar with the square law model of the MOSFET, which says that below the threshold voltage, when VGS is below the threshold voltage, the current is zero. It's not quite zero. There is another model for it. We'll look at that. And then you have resistors and capacitors. You also have inductors, but they are so small that they're useful only at high frequencies. So we won't go much into them. If you are taking or will be taking RFIC course at some time, you will see that you can use on-chip inductors as well. And then you have bipolar transistors and diodes. The emphasis will be on what is known as CMOS process, that is the process that provides both P and N type MOS transistors, because they are the most dominant technology used today. Okay, so our focus will be on that, but sometimes you need other type of components, and then you have those components available. May not be of the highest quality, but they are there nonetheless. And then it turns out, of course, these device models we go through, and then there are a number of uncertainties. That is, in an exam, of course, you are given the value of VT, you are given the value of mu Cox, and you calculate. It turns out these will have deviations. First of all, there will be systematic deviations. That is, if you fabricate an IC wafer today, and then 3 months later, they may be different from each other. And sometimes they deliberately skew the parameters to one side or the other to optimize. If you want to optimize for low power, maybe you will sacrifice speed, and vice versa. If you want to optimize for speed, you will have to live with a lot of leakage current and so on. So you have to, when you design an IC, you have to make sure that you design it across all these possibilities. Now, there is also some systematic mismatch that you introduce because of the way you physically draw the transistors, physically lay out the transistors. Those things we will look at. This is not, this won't be in great detail. If you take a course like IC design and testing, then you will be designing an IC, then you will get to know more of these things. But you need to know what this is, right? Because, for instance, the standard square law model says that the current is proportional to W and inversely proportional to L. It turns out that's not quite true. So that is, if you want to have the current, you can either have the W or double the length, but the two will not work in the same way. Okay. So if you want to have a current mirror with a certain ratio, you need to lay it out in a certain way. So those things we'll look at. Now, besides this, there is what is known as random mismatch. Even on a single IC, if you, in principle, the virtue of an IC is that if you make many transistors on an IC or many identical components on an IC, they'll have exactly the same parameters. But it turns out that the parameters will not exactly be the same. They'll be somewhat the same, but they'll be a spread. Okay. So you have to be able to analyze that spread and then make sure that you size the transistors or other components so that the spread is limited to whatever you need. Again, there are trade-offs between all these things. Okay. And there is also another type of uncertainty, which is random noise. Every device, I think you already know from the IV characteristics of the device, you know what the current should be for an applied voltage. But it turns out there will be some random component on top of this. You have to be able to calculate how much that is and quantify that. That's what eventually limits the performance of circuits. So that is something you need to know. Okay. And the other thing, I think something got dropped here. That is, you have to know how to analyze nonlinear distortion. Okay. And actually there is a subheading here. This, it's for op amps. So we'll have single-ended and differential op amps. The kind of op amp that you would have seen in analog circuits is what is known as a single-ended op amp. That is, you have a differential input and just one output terminal, and the output is defined with respect to ground. Whereas the preferred mode of implementation on an IC is fully differential. The output will also have two terminals, and the difference voltage between those two is the relevant signal. Okay. You need some special circuits to make those things work. We'll look at that. Okay. And in fact, the bulk of the course will be on designing the op amp. You have single stage, what are known as single stage op amps. You'll see what they are. I think you know that actually. Single stage op amp is a differential player is a single stage op amp. And you have multi stage op amp to have higher and higher DC gains. You can have 2 stages, 3 stages, and so on. Okay. And also fully differential, you have all these variants. There are so many variants, and you can come up with your own variants also. The main point is to understand the underlying principle, so that next time you come up with a basic amplifier topology, you can turn it into, let's say, you can use that in a single stage or a multi-stage op amp. And we'll also analyze mismatch and noise of op amps. I think you would have heard of offset of op amps. Ideally, when you connect an op amp in negative feedback, the input should be virtually shorted. In reality, there will be some offset between them. So the effect of that, and how, more importantly, how the underlying circuit affects the offset, that's what we'll look at. Okay. And other analog IC building blocks, I think this we will be able to do, voltage and current references. And if we have time, we will go into either phase lock loops or oscillators. Frequently, I find that we will not have time for that, but we'll see. Okay. Now, of course, the title also has the word design in it. So what is design and what is analysis? A design is creating something that doesn't exist yet. And analysis is analyzing something that already exists. Now, of course, in a course like this, there is a limited scope for design, right? We can only outline the design principles. Again, if you take a course like IC design and testing, then you will go through more thorough exercise of design. And then if any of you is pursuing research or a project in this area, you may also do this. Okay. Now, to be able to do design effectively, you need to know analysis, but it's not sufficient, because if you can only solve problems that are defined for you, then it will be difficult. You'll have to come up with solutions of your own, right? And what is important is multiple ways of looking at building blocks, because you're trying to make something that doesn't yet exist. So you have to try like multiple combinations and so on. So you have to become comfortable with some trial and error approach. Trial and error approach is not some arbitrary slapping together of circuits or something. It means, I mean, when you start with design, you can't start with every little detail that goes into the design, every little detail of the specifications. You have to pick the important ones, design for it, then analyze it, see if it really works the way you want. If it doesn't, you have to modify it. So that's the trial and error that I'm referring to. Then similarly, approximations, right? If you start a design by putting every detail into some big equation and then trying to solve for the variables, it won't work. Okay. And this intuitive thinking and understanding is important. This is not just for analog IC design. This is true for anything. If you want to do something well, you'll have to do it a lot of times and get an intuition for what is going on. And what is intuition? Basically, you have to be able to tell the answer without actually going through every step. Again, this is not about arbitrarily guessing the answer or something like that. Okay. You have solved enough problems of this type in enough different ways that you know which way the answer comes out. This is important for many things. First of all, you can't go and calculate everything in detail while during the design process because of many things. One is, of course, the number of variables is much more than the number of constraints you have. Okay. So unlike exam problems, we have n variables, and somehow the question will give you n constraints and you solve for it. So here you have to choose something based on your past experience and some good choices and proceed with that. Later, you have to use your analysis machinery to see if it works out or not. Okay. So you have to be able to somehow tell the answer without actually going through all the solution steps. But of course, then you solve it and see if the intuition is correct. So for this you can use deliberate practice. Whenever you are encountering a problem, you can first try to do this and then try to solve it formally and see if it matches. It could be that the solution is incorrect. Sometimes intuition works as a double check. It could be that the intuition is incorrect. Then you go and fix your intuition. That is, you figure out what is wrong with the way you thought, right? And of course, these things are curiosity and open mind and thoroughness are important for doing anything well. Okay. Now, I want to emphasize that intuitive thinking is not sloppy thinking. That is, it's not that, oh, I don't want to go through the bother of solving this, that's why I'll write something and that is intuition. No, that's not it. Okay. In fact, intuitively answering something is more difficult than simply writing down the equations and solving it. Okay. There has to be some reasoning behind it, right? And you would have used this, but deliberately practicing it also helps. Typically, what you do is you either relate it to problems that you've already solved, other problems. No two problems are exactly alike, but there may be something similar. And then you use some boundary conditions and dimension checks and so on. Okay. And you have to consciously build your intuition also by solving many problems, maybe solving the same problem in many different ways. There may be a time domain way of solving it. There may be a frequency domain way of solving it. These things are, I'll try to show some of these things. The point is you try to come up with the form of the solution before applying full-blown analysis. But then you complete the analysis and see, because your intuition also could be wrong. They have to see why that's wrong. Now, of course, you please take notes as you watch. Analog IC design is not a spectator sport. By listening to me, you will not learn anything. Okay, so you learn it only when you do it. You take notes as you go. Taking notes is not transcription. I have previous year's recordings which I have made available to you. So the idea is not to, let's say, write every word of what I say. Okay, you understand something and you abstract it for yourself in the notebook, and then you will. That's actually an aid in understanding. That's why you take notes. It's not for record keeping, right? Records I already have. I have like probably 8 or 10 versions of this course already recorded. Okay, and work out all the steps in solving the problem. You can see somebody else's solution, and you probably even understand every step when you see the steps. But the point is, when you have a blank paper in front of you, you have to reproduce those steps. How will you do that? You can do it only if you solve it yourself. And this is a standard formula. You expect to spend maybe 2 additional hours to understand each hour of lecture. Now we will be using simulators. Those of you who have access to the professional circuit simulators can use them. Cadence is what we use, people in our research group. Otherwise, I mean, the kind of problems we have in this are of the type that can be done in any free simulator. There is tools like LT Spice, which its new incarnation is called Q Spice. You can use this. There are tutorials. In the handout that I sent, it's already had links to some tutorials. Please start using them. How many of you have not used any circuit simulators before? Oh, everybody has used it. Okay, I could have skipped this slide. So, and then maybe you have to use MATLAB or Octave for some system level analysis. None of this will be very heavy, but you will need them. And then you can sometimes using a symbolic calculator can help. I gave a link to Maxima. Maybe some of you have used Mathematica. Whatever it is, again, the tool is not important. Sometimes the symbolic calculation, instead of going through a lot of complicated steps, you could use this to find the answer. But of course, the same rules apply. After you find the answer, you try to arrange it in a way that makes sense for you, right? Now, this I already told you. We have everything will be on Moodle, and recording. I'll try to record it and share it on Moodle as well. And there are a lot of previous year's lectures that are available to you. And this will be the evaluation. The 2 quizzes will be for 15%, exam for 40, and then assignments for 30. But you are expected to do your own work. If you get caught cheating, the penalty, there will be a significant penalty, and the penalty will go well beyond that particular assignment. It's not that there you will get 0 and nothing else will happen. Okay, and this will apply to both the source and destination of the copying. Moodle. Yeah. And these are all different references. There are some books, and we have our previous video lectures. Okay. Any questions at this point? Anything you want to know about the code? Yeah, it will be there. No, you can't submit. There will be a cutoff date, you can't submit. So before the deadline, whatever you have, you submit. I mean, it's called a deadline for a reason. Any questions? Huh? Whatever is in the lectures. Both. There'll be questions with analysis, there'll be questions with design later, of course, as you go along. See, our courses are structured such that based on the model, you can do everything. So you don't need the device physics. If you know it, it is good. But even if you don't know it, as long as you can start from the devices model of the devices, that is the IV characteristics of the devices, it's that's sufficient. And I think you've already done solid state devices. You're doing it now. Oh, okay. But you have done something equivalent. Yeah, you won't need. Okay, let's see. I'll very briefly introduce ICs. What is different about ICs than others? I mean, you would have not have heard of ICs before, probably. Oh. What is a CMOS IC? An integrated circuit is basically a piece of silicon or some other semiconductor material on which you have lots of components. That's what is meant by integration. Okay, so you have all the components in a monolithic structure that is on a single piece of silicon, and this is what has revolutionized this computing and communications and so on, right? Because you're able to make very large circuits which would otherwise be impractical. If you take individual transistors, resistors, and all these components and connect them together and make the modern computers, it would be impossible. So now there are ICs with billions of transistors, and it's because first the size of individual transistor has shrunk, and we've also learned how to make larger and larger integrated circuits reliably. That is, each transistor may be in the single digit nanometers these days, dimensions of 10 nanometers or less, whereas the size of the largest ICs will be in the tens of millimeters. So now you can imagine the number of components that can fit in. Okay. Now analog ICs can use older technologies also. There is some benefits. There are benefits of technology scaling that is going to more and more advanced processes, mainly for digital. But for analog, there are some advantages and some disadvantages. In any case, CMOS IC looks like this. This is a wafer of silicon, and typically you start with a P-type silicon wafer. Okay. Now you asked about device physics. This is the maximum of or most of device physics that we will look at. Not device physics, but at least just the structure of the device. So you have a P-type silicon wafer, and on that you make all your components. If you want to make an NMOS transistor, you make somehow create two regions of N-type doping. Okay. And then you have some oxide, and you have the gate. That is the gate of the MOS transistor. This is the drain, and this is the source. Now, one thing that will also be different from the MOS model you learned earlier is that very likely the MOS model you saw had only 3 terminals, but in reality it has a 4th terminal, which is also the bulk. Again, yeah, you would have seen this, but there is something special about the bulk here. The silicon wafer itself is the bulk connection. So if you have multiple transistors, the same bulk is present for all of them. So that means that the bulks of all the transistors are connected together. So that is one thing different about IC than discrete circuits. This is an NMOS, and if you want to make a PMOS transistor, within this you make an N region. It's called an N well, and within that you create these P islands, and you have the gate, drain, source, and the bulk. So this is NMOS, that is PMOS. And you can create any number of these things, but the main thing is with NMOS, you will have a common bulk. Now, sometimes you don't want this, so you create an N well. Again, there are many options. The very basic, when you say CMOS, it means complementary MOS, complementary metal oxide semiconductor. It means that it has both PMOS and NMOS type transistors. Okay, and typically with positive VTs, so that both can be turned off. Okay. Now, this is just to contrast from earlier processors which had only one type, had only NMOS transistors, and you had to do everything with them. But for a long time, we've had only the CMOS type. So these two will always be there, this one and other things are extra. So we could have, let's say within this, you create another P well, and within that, you make an NMOS transistor, drain, gate, source, and bulk. Now, in this case, this has a separate bulk. It need not be common with every other transistor. But this is a special process provision which you may or may not have. And this arrangement is called triple well. Well is another shorthand for bulk. So you have P and N and P. That's why it's called that. And then you will have many metal layers so that you can connect to these. And modern processes can have up to 10 metal layers, like stacked on each other. Okay. So once you have lots of these, first of all, this gate itself will be typically polysilicon, and then you have lots of metal layers. Okay. Right. So using these, you can make many components. So when you have a CMOS IC, you have PMOS and NMOS transistors. This is at least the very basic stuff you will have. And then you can make resistors in anything is a resistor, right? Anything that conducts is also a resistance, but of course the resistivity can be different. So it may be convenient for making some values of resistance and not others. Okay. You can make these in polysilicon or the metal layers. And you can also use the semiconducting layers. That is any of these N regions, P regions, this N well region and so on. Okay. Those also can be used as resistors. Only thing is they will be nonlinear. And you can have capacitors. Again, if you have any conducting layers in proximity to each other, there will be a capacitance between them. So you can make them using metal layers, and there are in particular two types of capacitors. We'll see the details later. Metal oxide, metal capacitors, and what are known as MIM. Basically, both are metal separated by some distance. And you can have inductors. Again, if you have a wire, you can make an inductor. You just make any wire will have some inductance. Okay, only thing is the inductance that you can get are typically in the single digit nanohenries and therefore are usable only at very high frequencies. The capacitors can be in the picofarad range, tens of picofarads at most. And also, in addition to these, you can also use the MOS transistor itself as a capacitor. You know, in fact, when you study MOS transistor, you start from the MOS capacitor. So that is there, right? So these are the basic components, and then you know that anytime you have N and P type semiconductors in contact with each other, it's a diode. Okay, so you automatically have diodes here, and also it turns out parasitic bipolar junction transistors. We'll see the details of these and device models, how the substrate affects them, etc., etc. Okay, so that's what we'll start off with. I'll stop at this point and continue from there.